Okay, today we will discuss, as I said, another very important supramolecular synthon, that is called crown ether. Crown ether. Synthesis of this compound, or rather discovery of this compound, was made serendipitously. Okay, it was not planned. But what happened? Charles Pedersen was a scientist in DuPont Chemicals in Switzerland, okay? And he was trying to make a diol with this particular compound. I will show you. First, let me draw the picture. Many of these compounds were serendipitously made. So, they have all stories behind their discovery or behind their synthesis. So, this is a compound, okay? A cyclic ether here, and this one also oxygen bridge. So, from here he took this particular dichloro compound, all right. Yeah. So, he wanted to make, okay, this is saturated, all right. So, this can be easily removed. He wanted to make a diol, a linear kind of diol. So, he treated that with sodium hydroxide in tertiary butanol solvent. Tertiary butanol has a higher boiling solvent. So, you can go up to higher boiling point, followed by acid quench in aqueous. So, it will precipitate out. Okay. All right. So, he wanted to get this for his other work. All right. So, he wanted to get this diol was the intended synthesis. He wanted to get this diol from this compound, okay, monohydroxy compound, and is a dichloro compound. So, he reacted. Now, in this particular compound, it was made from catechol. So, he had some unreacted catechol as impurity in the mixture. So, he had, this is catechol. This is catechol. So, he had this catechol in the reaction mixture, that was unreacted, it did not convert 100% to this particular compound. So, when he got this, so he had this little bit. So, this reacted with dichloro, a very small amount. Okay. and with the same a very small amount. So, he got something, some yellow product, yellow something oily product, and what you will do? Most of the time we will throw it and get our intended dihydroxy compound and be happy with it. It has one more carbon. Oh, okay, all right. And here also same thing. He got this particular compound. He got this macrocycle. So, in order to make this diol linear, he cooked it with this dichloro compound and he synthesized this one from catechol. This is catechol. So, some unreacted catechol as impurity, it reacted with this dichloro and came this. This is a very small amount, okay. Say 1%, and he understood that. He understood that yellowish oily compound at room temperature and in that solvent system. He found that there is something new in this here. Most people will throw that. Most people will throw such compound, but he was a very hard working person and he did not quit. So, he says Pedersen could, I am telling his words, Pedersen could recognize he was on to something important with subsequent characterization of this compound as colorless compound. So, he isolated this as 0.4%, that means a very small amount, and this is 99%, over 99%. Okay. So, we will actually filter it out and will be happy with this compound, but not him. He said, what is that yellowish thing? Let me isolate. He isolated and found this compound. So, this compound is known as dibenzo 18 crown 6. So, this is a dibenzo 18 crown 6. 18 crown 6. The name he gave like this, there are two benzene. So, dibenzo and 18 means there is 18 member, 1, 2, 3, 4, 5, 6 like that 18 members. So, that 18 membered and is a 6 means 6 oxygens are there, ethereal oxygens are there. So, it is dibenzo 18 crown 6. He serendipitously synthesized this particular compound, all right. And what happened? He wanted to, since this compound is a nice and macrocycle, so he wanted to find a probe its complexing ability with metals. To his amazement, he found that alkali metals readily form complexes with this, and he found that potassium can be crystallized, where a potassium ion inside this macrocycle can be crystallized. Before that, it was not known that there was no coordination chemistry of alkali metal compounds known with macrocycles, with anything. So, this was the first compound of potassium complex. So, because of this discovery, he got the Nobel Prize in 1987. So, you can understand that this is not a simple compound. He got Nobel Prize because of this simple compound. So, these compounds are collectively known as crown ether. Let me draw some pictures of crown ether. So, let me draw some pictures of crown ethers to appreciate. So, crown ethers are mostly ethylene bridge. There is an ethylene moiety between two oxygen. This is here is a 15 crown 5, 15 crown 5, okay. This is a 15 crown 5 and this is 18 crown 6, you can write. This is 18 crown 6. So, there are numerous compounds of crown ethers are known since then, all right. And what is their property? Depending upon the size of this macrocycle, they can complex different alkali metals. So, this was the beginning of alkali metal coordination chemistry. So, that is a very, very important phenomenon, all right, very, very important. So, that was Pedersen discovery was the beginning of coordination chemistry of alkali metals, all right. Now, synthesis, since then, now that we know this kind of compounds exist, so let us can exist. So, let us look at some of the synthetic methods adopted by people. So, the principal, so the first method that Pedersen used is still operational. First method that Pedersen used was this, right. We can say this is a this is like a ethylene bridged, so dihydroxy compound or ethylene glycol say plus say chloride and then space chloro with a base, and of course, you have to reflux it in a suitable solvent and you get S1 this, okay, or you can get two of these say S2 chloro again reflux with base. Let us see. Like this. Okay. So, many things he got, and then he also found that when depending upon the base, the yield of this product depends. So, suppose I want to make 18 crown 6, he found that if you take potassium tertiary butoxide, I will draw it here, small amount. Let me draw. You take this kind of linear parts. This is a diol. With this diol, you can say tosylate. Tosylate is a good leaving group. So, you can get this. Okay. Tosylate. Plus, if you now instead of hydroxide, you can say tertiary butoxide. Potassium, tertiary butoxide, and then what happens? You get this compound with potassium. It is a very strong base. So, if you react this, you will get O minus and so we discussed about template. So, potassium is also being used here as a template, and then it can easily make let us see tosylate I have made a mistake. This is 1 oxygen, tosylate. Okay. So, could react there and this could react here, and you get ultimately you get this compound very beautifully. With a very good yield also. Potassium. Potassium in there. Okay. So, there are many crown ethers were synthesized, and some of these structures I will share with you. These are any book you can get. For example, you have this, you take a dihalide basically and a dihydroxo, linear dihydroxo compound. In base you will get different kinds of crown ethers. For example, no. Okay. I am just showing you some example. It is not nothing extraordinary, but it is good to show what the structure, some of the structures known. Okay. So, this one ditosylate, and another molecule will come from this side, another molecule will come from this side. Okay. All right, and then you react it with butanol solvent and butanol followed by LH, and you are ended up with this huge. So, I am drawing only this, others I am not going to draw, but there are many. I just wanted to emphasize that different kinds of structures are possible to synthesize different kinds of molecules. Okay, this is 1, 2, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. No, it is a meta. My joining was not right. I will make it right. Okay. So, this is the compound you can synthesize. This compound is not looking world's most beautiful structures that I have drawn, but at least you can know that there are how many oxygens? 5 above, 1, 2, 3, 4, 5 and 5 below, and then hydroxy also there. Under these reactions they can methoxide, this group will change to hydroxy group. So, you can get this kind of compounds. That means, I am trying to drive home that not only the simple crown ether compounds, but you can get crown ethers of varied structures. Okay? All right. Next, not only the crown ether, I will show you another compounds are there also. Mixed crown ethers like Aja crown ethers, these are also formed. So, what I am writing one after another these molecules, these are synthesized by different people, okay, and these are supramolecular synthon. How to use them, that we will describe slowly. We will just use it and we will describe slowly to you, so that you can you may not appreciate what is the need of making this compound. Well, we have to show you what can be done. So, these designs are compounds of different designs that you can appreciate. So, first what I am trying to do, I am trying to make different compounds, synthesize different compounds like this Aja. So, this is Aja crown, okay, because you have two secondary amines are also there in this ring. Then we can have this compound. So, you can many. It is not my aim to put one after another, but to drive home the message that we can get compounds of our liking, no problem. Different kinds of compounds, all right. Azacrown, completely azacrown you can get. You can get like this, is only azacrown, or you can get this 12 member, and this particular compound is very important. It is called cyclam. It has been found to use in many cases. You can realize that I am trying to make these macrocycles of different sizes. Why? Our aim in the beginning, the aim of supramolecular chemist, or rather chemist, was to synthesize macrocycles of different sizes, so that we can bring in specificity of binding, all right, specificity of binding. If you have if these are nitrogen crown ethers, then they bind transition metal compounds. If these oxygen or our crown ethers, they bind alkali metals. Now, if we can synthesize a particular macrocycle, design it such a way that it can specific binding, that is the key word, specific binding. Specific binding. If you can specifically bind a particular metal ion, then it will be tremendous. For example, suppose there are so many metal mixture is there. I like to bind only nickel 2 plus from this. We have copper, nickel, zinc, okay, all kinds of metal ions there in a solution. If I can specifically bind say nickel or specifically bind potassium ion, so that they can be separated, then it is great. We can do many things. So, what things, why it is important? Slowly it will be obvious to you. So, in the beginning it was the aim for all of us to make these compounds of different sizes and different donors. Okay. So, I will stop here today, and then again I will deal with something else. Okay. So, what I am trying to make? Macrocycles to bind different metal ions. Thank you.